talk by introducing Gillian, which is a tool that my colleagues of mine have made in the past. And it's what they call a parametric compositional symbolic execution framework. It's a bit of a mouthful, but it's basically a symbolic execution tool with a number of features. For starters, it's parametric on the memory semantics of the language you want to analyze. So if you want to analyze C programs, then all you need to do is provide a C memory model to Gillian, and now you have a tool that can analyze C programs. And you can do the same thing for other languages like JavaScript. So just provide a JavaScript memory semantics to Gillian, and now you have a tool that can analyze JavaScript programs. It's also compositional in the sense that rather than, yep, that's right. Okay, right, yeah. Sorry. Hello? Is it all right? Yep, right. Cool. Yeah, so it's compositional in the sense that rather than analyzing the program as a whole, you analyze the program by its parts. And specifically, it's about functional compositionality. So we analyze function by function. And we acquire the specifications of the function and use these specifications when we encounter a function call in the future. So it makes analysis a bit more scalable. And finally, there's another feature that's absent in other similar tools like Vipe or VeriFast. And it's the ability to do not only separation logic-based specification verification in an over-approximate style, but also incorrectness separation logic-based automatic specification synthesis through biproduction, which is an under-approximate analysis. So Gillian's pretty versatile, and it has been successful in terms of analyzing real-world code in the past. So it's been used to analyze some C and JavaScript libraries through symbolic testing. And through separation logic-based verification, it's also been used to verify AWS code and some standard library code in Rust. So it's pretty great. But at some point, we stopped and took a step back and started asking a question. Why does it actually work? How do we know the tool is actually sound? Or better yet, what does soundness mean in the context of Gillian or even any symbolic execution tool, compositional symbolic execution tool? So to address this, there were some attempts to provide a formal, foundation for compositional symbolic execution tools in the past. But there's a number of problems with these works. So for starters, it's these works are tailored specifically towards Gillian. So it's not really interoperable or compatible with other frameworks like VeriFast or Viper. And the formal foundation only covered over-approximate based analysis and not under-approximate based analysis, right? Also, the memory model instances were not proven to be sound. So when it comes to like the C memory model or the JavaScript memory model used in the previous works, we just had to trust that the implementation was done correctly by the devs. And finally, it's not mechanized. So you had to kind of trust that the pen and paper formalization was correct. And so this is where our work comes into play. We introduce our what we call the CSE theory, right? So it has the following features. So it's parametric on the memory model, just like Gillian. But now we have a memory model theory. So we have properties on top of the memory model. We also have a general foundation, formal compositional symbolic execution foundation for not only separation logic based analysis, but also incorrectness separation logic based analysis. And to show that we have a sensible theory, we instantiated a number of various memory models. So it kind of ranges from something very simplistic like the linear memory model to something a bit more substantial like a capability hardware enhanced model. And finally, it's mechanized in Rock. So you don't have to trust that our theory is correct. It's certified by a theorem prover. So for today's talk, I'm just going to briefly touch some key aspects of our CSE theory. And in particular, I'm just going to introduce the engine. and introduce how how we would formulate and attempt to prove the soundness property. I'll also show how we would instantiate a linear memory model during this process. And if we have the time, I'll briefly talk about some of the other instantiations. So let's start with the theory. As I said, the main component is the CSE engine. And if you kind of zoom in, we have the symbolic semantics, which is pretty standard of symbolic execution. And because we're dealing with functional compositionality, we need a way to use function specifications during function calls. So we have an assertion language, and we have the symbolic semantics depend on the assertion language. And finally, to ensure that we have a soundness theorem stated, we have the concrete semantics. And really the idea is that we link between the symbolic semantics and the concrete semantics. Right, so that's the overview of the CSE engine. And to deal with memory-specific stuff like memory actions and spatial resource assertions, this is where the memory model theory comes into play. So if we zoom into the memory model theory, we realize we have a structure that's pretty symmetric to that of the CSE engine, right? So if you kind of look at it from bottom top, we start from the concrete memory model. So here we define the data structures, semantics, and properties of the concrete memory. Just to give an example of instantiation, if we consider the linear concrete memory model, the structure of this would just simply be a mapping from locations to bytes, location to values, right? The next level is the resource model. So here we actually define the spatial resources of the memory. So it's just defined by this resource predicate, and we define what it means for this resource predicate to be a model with respect to the concrete memory. And for the linear memory model, the way we define the resource assertion for this would just be a standard points to predicate. And we also provide a way to relate this to the concrete memory by saying we have a concrete memory with exactly one mapping from ins to outs. And then finally, we have the symbolic memory model. So it comprises the data structure and the semantics, but it also provides a way to remove or add resource assertions from and to the symbolic memory, right? So for the linear memory model, the memory structure is just a symbolic lifting of the concrete counterpart. And for the two operations that remove and consume and produce, it's about either removing a cell assertion from the symbolic memory, or it's adding a cell assertion back to the symbolic memory. All right, and then finally, to make sense of these operations, we need to have some kind of soundness theorem, soundness statements. So here we actually state what it means for these operations to be sound. And the instantiation is about actually proving the soundness of these operations. So here's the important part. So we have the soundness statement of the memory model, and we're going to use this to prove the soundness statements in the CSE engine, right? So that's the idea. So now, how do we define and attempt to prove the soundness theorem in the CSE engine, right? The basic idea is that if we assume we have a symbolic step, right, and the final symbolic and concrete states are related by somehow, then there exists an initial concrete state such that there's a corresponding concrete step, and the initial states are related, right? So in other words, it's essentially saying that we have a symbolic semantics that under-approximates the behavior of the concrete semantics. So usually we now have the soundness theorem, and if we want, so we would usually do structural induction over the symbolic semantics, and perhaps the most interesting case to consider is the function call case, right? Which is kind of what the CSE standard CSE tools like Gillian, Viper, and VeriFast would do. So first, it's important to understand how the function call works in the symbolic semantics. So let's assume we're trying to call a function, and we're in the symbolic state sigma. And let's also assume we have the specification of the function, right? The idea is we want to match part of the symbolic state that corresponds to the precondition in the function specification. Once we this operation is the matching process is done through this consume operation, right? So once we find a match, which is this sigma p over there, we're going to remove it, and then we're going to generate a new symbolic state that corresponds to the postcondition of the function, and then we're going to add that back to the final state. So that's essentially the idea behind the functional call semantics. And so here, these consume and produce operations, we didn't set a specific implementation. Rather, we made it parametric, since there's already prior work that allows us to define the properties of these consume and produce operations. So here it's saying, we have these two operations, and we can define the properties through some soundness statements, and we can use this to prove the function call case for the soundness theorem. But there's a problem with this work, because what happens if we have spatial resources in the specification, right? It's a big problem because this work is not parametric on the memory and spatial resources, so it's fixed on the linear memory, and so we need to find a way to generalize this work a little bit more. But if you take a step back and go to the memory model theory that we had before, that I introduced before, we realize that we have these consume and produce resource operations. So this is specifically for spatial resources. And we also have behaviors that, we also have properties that state the behaviors of these operations, right? So going back here, the way to tackle this issue is to use the specific consume and produce resource operations. And in terms of proving soundness, we can still use the consume and produce algebraic interface that was done before, but we extend this work to support the consumption and production of resource assertions. So there's many more interesting cases to consider, but more of the details of those cases are in the paper. So yeah, that's the overview theory, and I just want to briefly touch on the some of the instantiations that we had, right? So I already kind of described about the linear memory model instantiation, but for the other ones, we also proven some more interesting ones, and we've proven them to be OX and UX sound. But perhaps it's worth pointing out that there's a more substantial one called the cherry memory model. For this one, we proved it to be OX sound, but we're still working on the proof behind the UX soundness. But you can see even just proving for the OX case, it takes about 19,000 lines of code, which is a big effort. But really, the point is to show that our CSC theory is capable of instantiating more serious memory models. So to conclude the talk, we have this general mechanized parametric compositional symbolic execution framework. In the future, it'd be nice if we could kind of have some kind of library that eases the instantiation effort of these memory models. So currently, we just kind of have to build everything from scratch, and it takes a lot of time to kind of get everything to work. And eventually, it'll also be nice if we could instantiate other memory models that's already in Gillian. So there's more details in the paper, and if you're interested in the actual formalization, it's also available online. So that's the end of my talk. I'll be happy to answer any questions. Thank you.
Not any question, just one.
All right, cool. Yeah.
Yeah, thank you for the talk. Microphone's turned up too loud. The symbolic execution engine is parametric on the memory model, but it looks like for the soundness result, you're relying on the symbolic memory model that you created, the operations that you defined on the symbolic memory model. So the soundness proof still relies you to have picked an instantiation already. You don't have a parametric soundness proof.
So with the memory model, you still have to define the memory semantics and the actions and the properties, and then you have to define the soundness over these over those semantics. But once you have that, then you can use that to prove the general soundness term in the CSE engine.